Good day, doctor and everyone. We are Group 3 and today our presentation is on membrane separation electrodialysis, which is one of the key applications in electrochemistry. My name is Pavitra and together with my teammates Ayman, Fatini, Tarvina, Cheezen, Jingzi, QJ and Bengi, we will be explaining the fundamental principles, applications, advantages, limitations and innovations related to electrodialysis. To begin, I will first introduce the overall concept of membrane separation electrochemistry. Membrane separation electrochemistry is a field that combines membrane technology with electrochemical principles. It is mainly used to separate components from liquid or gas mixture using selective membranes. The separation happens because semi-permeable membranes control which ions or molecules can pass through while an electric field acts as the driving force. When voltage is applied, ionic species move according to their charge, which allows very targeted and efficient separation. In some cases, electrochemical reactions at the electrodes also help the process. One of the key techniques in this field is electrodialysis. Electrodialysis uses alternating cation exchange and anion exchange membranes, and it relies on electricity to remove ions from a solution. This is the main method we will be discussing in our presentation.
Now let's look at electrodialysis. Electrodialysis is an electrochemical separation process in which ions are transferred through ion exchange membranes by means of a direct current voltage. The process uses a driving force to transfer ionic species from the source water through cathode and anode to a concentrate wastewater stream, creating a more dilute stream. So basically, electrodialysis is an electrochemical separation process that uses electric field to move ions out of water. When you apply voltage across a stack of special membrane, cations will move one way and anions move the opposite way. It separates a stream of water into a dilute stream and a concentrate stream. Next, let's look at the components of electrodialysis unit. Electrodialysis unit consists of ion exchange membrane, electrodes, power supply, and spacers. Ion exchange membranes arranged in alternating sequence where cation exchange membranes allow positive ion to pass through and anion exchange membrane allow negative ion pass through. Next, electrodes. Electrodes are placed at the end and create the electric field when connect to a power supply. Third, power supply. Power supply is a direct current power source that provides the voltage across the electrodes and drives the movement of ions. Lastly, spacers. Spacers are non-conductive structure that place between membrane to ensure proper water flow and prevent the membrane from clogging. As you can see here, there is a feed solution. Feed solution is the initial water or solution that enters the system to have ions separated by an electric current. It flows through a series of compartments created by alternating cation and anion exchange membrane with an electric field to drive the ions across the membrane and create separate streams of diluted and concentrated solution.
Electrochemical principle. So what is electrochemical? Electrochemical is the idea that chemical reactions and electrical energy are connected and can be transformed into one another through redox processes. There are three principles of electrochemical. First, we have oxidation reduction. It is the transfer of electrons between two chemical species, and we know that oxidation is the loss of electrons and reduction is gains of electrons. Next, we have the electrical conductivity. Electricity enters or leaves an electrochemical system. Anode is where the electron or oxidation occurs, and cathode is electrode that where reduction occurs. And lastly, we have the energy conversion. It describes how controlled reaction either employ electricity to create chemical change or transform chemical energy into electricity.
About my slide is all about mechanism of electrodialysis. So this system are using direct current, which is DC, and ion exchange membranes to separate ions from water. So when voltage applied to it, cations are migrating to cathode while anions are migrating to anode. So about ion exchange membranes, it selectively allow either cations or anions to pass because as you can see there to the picture, to the diagram, there is an ion selective membrane and there's also a cation selective membrane. So moving on, alternating membranes create two compartments, which is dilute compartment and concentrate compartment. Where dilute compartment, the ions are removed, while for the concentrate compartment, ions are collected. As you can see in the diagram, there's two output, which is freshwater and concentrated brine, where freshwater are the dilute compartment and concentrated brine are the concentrate compartment. This process repeats across multiple cell pairs for efficient desalination or demineralization. There's no chemical reaction, it just relies on ion mobility under electric field. Okay, now we're talking about ion exchange membranes. It is act as a selective barrier that allows only certain ions to pass. There are only two types used in electrodialysis, ED, which is cation exchange membrane, CEM, that only allows positive ions and block anions, while anion exchange membrane, AEM, doing the opposite, which is only allow negative ions and blocks cations. It is arranged alternately between electrodes, prevents ion from returning to the dilute stream, or just in the other hand, ensure one directional flow. It is to one of the functions of it is that maintains charge balance while keeping compartments separated. It is also critical for high efficiency, ion purity, and water quality in ED systems.
Slide, we're going to see about the electrodialysis configuration. So first, for electrodialysis, the main structure is the ED stack, which is made of alternating cation exchange membrane (CEM) and also anion exchange membranes (AEM). This arrangement forms the dilute and concentrate channels, allowing salts to be removed from one stream and collected in the other. Next, we have electrode compartments. At both ends of the stack, there are electrode compartments containing anode and also cathode. These electrodes create the electric field that drives ion across the membrane. Then, lastly, we have a popular configuration which is called electrodialysis reversal, which we can also call as EDR. In EDR, the system regularly switches the polarity of the electrodes. This causes the dilute and concentrate parts to swap. This will help minimize the fouling and scaling, which will be helpful to the membranes to last longer and the system to run more efficiently. So for the next slide, we're going to see the performance of an electrodialysis system, which has its several key performance. So one of the key performance is current efficiency. This current efficiency indicates how effectively current is used for ion transport. Next, another important factor is specific energy consumption, which tells us how much energy is needed to treat each cubic meter of water. We also can look at the water recovery and salt removal to determine how much product water is produced and how effective the distillation performance is. Then we have the membrane properties, which is conductivity or resistance affect ion migration and energy use. Next is selectivity. Selectivity and perm selectivity affects ion separation quality. And we also have falling scaling resistance impacts the long-term performance of a membrane. And finally, we have operating factors such as current density, voltage, flow rate, feed salinity, and all affect mass transfer and energy demands. So this influences how much salt is removed and how much energy system is needed.
For this slide, I will explain how electrodialysis is used for brackish water desalination. This is the process of removing salts and other minerals from brackish water to make it potable. Brackish water contains a moderate amount of dissolved salts. Some common ions found in this water include cations such as sodium, calcium, magnesium, and potassium, as well as anions such as chlorine, sulfate, and bicarbonate ion. Because all of these are charged ions that are suitable for removal using the electrolysis process. When an electric field is applied, cation move towards the cathode and pass through the cation exchange membrane, while anion move towards the anode and pass through the anion exchange membrane. These movements separate the water into two streams. A diluted stream where most of the ion has been removed and become fresh water, and a concentrated stream where the ions accumulate. Electrodialysis is considered energy efficient for treating brackish water because the salt concentration is not too high. Studies show that operating electrodialysis at around 6 watts can already achieve effective salt removal with low energy consumption for about 1.65 kilowatts hour per cubic meter of water treated. So overall, electrodialysis is an efficient and practical method for producing drinkable water from brackish water by selectively removing ions to an electric cell. Besides, electrodialysis can also be used in industrial wastewater treatment. Many industries produce wastewater that contain different types of contaminants. One major category is heavy metal containing effluents, for example nickel, copper, and zinc, which are commonly produced by plating, tanning, and metal fishing industries. Besides heavy metals, some industries also discharge salty or saline waste streams, which include high levels of salts, acids, bases, or mixed salts. In addition, many industrial wastewater contain complex mixture of different ions, making them difficult to treat using traditional methods. Electrodialysis is useful in this situation because it separates ions effectively. When an electric field is applied, an ion migrates towards the cathode and passes through the cation exchange membrane, while an ion migrates towards the anode and passes through the anion exchange membrane. This movement splits the wastewater into two streams: a diluted, which becomes cleaner as ions are removed, and a concentrated, that ions and pollutants are collected. The treated diluted streams becomes low in ionic content, which allow the industries to recycle the water for cooling, washing, or process reuse, and reducing freshwater consumption.
The application of electrodialysis in food and beverage industry. First, we have the wine stabilization, where we reduce the tartrate stability of the wine by removing the tartrates and potassium from the raw wine. Next is pH adjustment of wine, where we modify the wine's natural acidity to produce an outstanding flavor. We also have juices and ciders pH adjustment, where we alter the fruit juices pH, which has a big impact on the organoleptic quality. We also have the purification of organic compound, where we reduce the amount of salt in the finished product by eliminating the ash content from the feed solution. There is also application in sugar industry, where purification occurs with low energy and chemical consumption. There is also starch syrup purification, where effective demineralization method without overuse the chemical. There is also the molasses processing for the beet and canned sugar mills, where we treat the feed solution in order to remove as many unwanted carbohydrate contaminants as possible. And lastly, in dairy industry, it is demineralization, where we reduce the amount of salt in the finished product by eliminate the ash content from the feed solution. So this is the application of electrodialysis in food and beverage industry.
So now I'm going to present about the advantage of the electrodialysis. So first, the electrodialysis has high resistance to scaling and fouling. This means the membrane do not get dirty or block easily, especially when the system reverse is protected. So it only needs a lower maintenance fee, longer membrane lifespan, and fewer cleaning years. Second, the electrodialysis allows selective ion removal, which can reduce the operational cost. Since the energy and cost of electrodialysis depends on how many ions are removed, so it can only target specific ions such as sodium or calcium. This makes the process more economical compared to methods that remove all ions equally. Third, electrodialysis is highly suitable for low total dissolved solid brackish water. The article highlights that electrolysis performs best in this range, making it very useful for treating brackish groundwater, especially in regions where drinking water sources are limited. And fourth, electrolysis has feasible application across various industrial processes. It can be used in brackish water desalination, RO concentrate recovery, salt production, and even citric acid separation. So overall, electrolysis stands out due to its resistance to falling, cost-saving, selectivity, suitability for low TDS water, and wide range of applications. So now I'm going to present about the limitation of electrolysis. So first, electrolysis has high energy consumption and operational cost. The energy requirement increases when the Fi voltage or ion concentration is high, and it becomes even worse when flooding occurs. Because of this, the overall operation cost rise significantly, mainly due to both membrane folding and the high energy demand. Second, membrane folding is a major challenge. Organics, colloids, and biomass tend to accumulate on the membrane surface, which increase membrane resistance and reduce the selectivity and separation efficiency. But there is also the issue of metal precipitation on the membranes. For example, cadmium can precipitate onto cation exchange membranes. This blocks ion transport pathway and directly reduce the effectiveness of the electrolysis process. Finally, electrolysis requires pre-treatment to reduce folding. Factors like pH, flow rate, colloid concentration, and raw water composition can strongly affect membrane performance. Proper pretreatment is necessary to protect the membranes, but this adds extra complexity and increase the overall cost of the system.
Let me share about the impact of electrodialysis from the environmental aspect. So for the positive aspect, electrodialysis can produce the brine through desalination without causing damage to the water ecosystem. Therefore, it can support sustainable water reuse. Electrodialysis also reduces the chemical use for ion removal. For the negative aspect, as the salinity increases, the energy required will also increase. Therefore, it will cause higher energy consumption. The byproduct of desalination, which is a large volume of concentrated brine, will cause environmental issue if it was not disposed properly. So for the economic aspect, the positive side is that the operating cost for low to moderate salinity water is low. Besides that, the reduced consumption of chemicals also reduce the cost. Not just that, it can also support the circular economy by turning waste streams into usable products. You can look over here. This is the circular economy. So for the negative impact, the fouling membrane will increase the cost of cleaning, pre-treatment, and maintenance. Right over left here, it is a fouling membrane. Besides that, the disposal of concentrated brines will also add the cost. So now let us learn about the future trends of electrodialysis. So the future will point to advanced ED by coupling with other technologies to increase its sustainability. For example, reverse electrodialysis and photovoltaic, which have been presented as possible solutions to sustain electrodialysis desalination and promote a cleaner production. So as a conclusion for our presentation, electrodialysis is an effective membrane-based technology for selective ion removal, desalination, and resource recovery. It will offer advantages, and economically, electrodialysis is the most favorable for low to moderate salinity water. So while the challenges like membrane folding and concentrated disposal remain, it continues to advance and remains a promising technology for sustainable water treatment. So here are the references we use in this presentation. So that's all from our group. Thank you for watching this video.